For decades, mainstream neuroscience has treated dreaming as a nocturnal filing system, a process of memory consolidation or emotional regulation. The Brain Kinematics Model, or BKM, proposes that dreaming is an active, forward-looking computational engine. During the day, waking cognition is highly constrained, relying on strict logical rules. During sleep, however, the brain shifts into a low-constraint, exploratory mode. This loose environment provides the necessary space to process complex cognitive problems that cannot be resolved within a single, rigid waking domain. Dreams operate as dynamic simulation spaces, computational arenas where the brain untangles the contradictions carried over from our waking lives. This computational shift maps high-dimensional, abstract ideological tensions into lower-dimensional, actionable scenarios. These two concepts share a topological equivalence. The structural relationship between competing forces remains identical, even as the setting changes. We can observe this mechanism at work in a documented 2-night dream sequence. The subject goes to sleep wrestling with a massive question: the optimal balance between capitalism and socialism. To process this, the brain employs a finite-element simulation, breaking down a massive structural problem into small, manageable pieces to calculate localized stress. By running these simulations, the dreaming mind tests specific interpersonal behavioral solutions for resolving global imbalances. Cognitive tension is a deviation from balance. Delta E equals the absolute value of E minus E0. This warped 3D topography shows high total strain. One vector is capitalism's efficiency gradient, striving for localized gain. Opposite is socialism's equity gradient, pushing towards distributed balance. Maximizing localized efficiency and global equity simultaneously creates a persistent non-equilibrium condition. The waking brain, bound by strict logical rules, lacks the necessary degrees of freedom to process a contradiction of this magnitude. Because waking cognition cannot minimize this total strain gradient, the brain shifts the problem into a different domain to prevent cognitive deadlock. Sleep initiates a mechanical shift. The system enters a low-constraint mode to redistribute that unresolved strain, collapsing a complex ideological gradient into a simple social interaction. In the first dream, the subject explains to his religious father that drinking wine is normal in the West. Mapping this, the father represents absolute ethics. The wine is relative context. The tension between them becomes a direct strain over moral judgment. The dream uses this scenario to test how we navigate and judge behavior when two background value systems clash. Waking thought asked a massive question about organizing economies. The dream translates this into how to explain a cultural norm to a parent. At this stage, the brain has reformatted the abstract political tension into a localized moral judgment, significantly lowering the complexity of the problem. The next night, the simulation iterates the same variable. In Dream 2, the subject is a competent manager who helps another boss's project discreetly. We map this new scenario exactly like the first. The project boss represents rigid hierarchy. The subject's technical assistance is the competence vector. The tension is a strain over professional recognition. The subject's high productivity directly threatens the other boss's authority, risking the stability of the hierarchy. To resolve this, the subject executes a behavioral solution, providing necessary technical help but remaining discreet to avoid triggering defensive instability. The brain is calculating that efficiency and correctness are practically useless if the method of applying them destroys the authority structure meant to receive them. Looking at the waking state and both dreams, these are three scales of the same computational problem. We align individual strength, efficiency, context, and competence down the left. On the right, system preservation, equity, absolute ethics, and hierarchy. The total cognitive strain is preserved. While the total energy of the problem remains intact, the radical reduction in complexity allows the brain to work with solvable variables. Political philosophy, professional diplomacy, and personal ethics are functionally the identical equation, computed at different scales of abstraction. Continuity theory dictates that cognitive systems seek an axis of balance, but they must maintain active gradients to prevent the system from stagnating. In the subject's waking ideological problem, the risks are clear. Over-indexing on capitalism creates heavy inequality strain, while over-indexing on socialism creates stagnation strain. The dreams function as finite-element nodes. They act as temporary, localized points of equilibrium nested within a massive waking imbalance. A universal behavioral principle emerges from these nodes: maximize individual contribution while minimizing disruption to the broader structure. This specific behavioral rule operates as a dynamic balance point, avoiding the extremes of either pure ideology. Dreaming acts as a phase space mapping tool. It gives the brain a secure environment to test micro-solutions before they are applied to macro realities. The BKM framework carries strong predictive implications. If the waking strain persists, subsequent dreams will begin testing the failure cases. These simulations might explore what happens if the subject openly dominates the other boss, resulting in conflict, or what happens if they remain passive, leading to system inefficiency. The simulation can also scale up, introducing multi-agent dynamics to test how these same balance principles operate at the level of a team or a broader society. This leads us back to the original waking question regarding the balance between capitalism and socialism. Optimal systems, whether in the human mind or the global economy, are never defined by a static ideology. They operate as an active, ongoing process. True socioeconomic and cognitive balance is the intelligent, continuous redistribution of strain across a system, maximizing function without breaking its structural coherence.